Hello, everyone, and welcome to lecture 11 of GPU computing. Today we're going to start talking about new parallel pattern, which is scan. And in particular, we're going to look at a specific approach to parallel scan, which is the Kogge-Stone algorithm. And next time, we'll actually look at a different approach for doing parallel scan. But before we start, just a quick review of what we covered last time. Last time, we looked at reduction. We said that a reduction is an operation that takes a set of input values and reduces them into one value by some kind of operator, such as sum, product, min, max. In general, this operation should be associative, commutative, and have some kind of identity value. And we used sum as an example, but the same thing that we learned applies to the other operators like product, minimum, or maximum. A sequential reduction for sum would look like this. You would initialize the sum to 0, and then you would loop over the elements of the input array, and you would accumulate them to the sum accumulator. In general, if you're doing a reduction, you would initialize the sum accumulator to the identity value, and then you would loop over the inputs elements in the array, and you'd apply the operation to the accumulator and the input value, and put the result in the accumulator. So, for example, if this was max, the identity would be the absolute minimum, and then the f over here would be the max operation. We then looked at how to parallelize this, and we said that one way we can parallelize it is by, if we have a certain set of inputs, we have, we have half the number of, we have half the number of inputs and threads, and every thread is responsible for adding 2 elements, and that reduces the number of input values we have in 2. And then we have a number of threads to again add 2 elements in each thread adds 2 elements all in parallel, and then we have half the number of elements again, and we keep doing this until we have the final result. And we saw how we call this a reduction tree, and what we can do is we can add n elements in log n steps in parallel. But we saw that we need to have a global synchronization across threads on every iteration, because the threads need to wait for each other to finish, because in the next iteration, one thread is going to have to use the result of multiple previous threads. And because this operation requires this kind of synchronization, we usually solve it in a segmented way, where we take the input, we segment it, every thread block does a reduction tree locally, and then they store the partial sums somewhere, and then we go and reduce these partial sums either by having a new reduction kernel that reduces these partial sums, or using atomic operations, which we'll cover later, or by adding them on the CPU. And the reason we do this is because we can't have global synchronization across different thread blocks, so we can't just have one big reduction tree across the entire GPU. We looked at different ways of doing a reduction tree within a thread block. The first and perhaps most intuitive way of doing it is like this. We had a thread assigned to every other element, and this thread first would add the element these threads would add the elements that were 1 away from each other, and then every other thread would add elements that are 2 away from each other, and then we keep going until we have one final result. But we observed that this approach is not very good for memory coalescing and control divergence, because every time we have every other thread dropping out, and also when the threads are accessing data, they're accessing it in a strided way. So what we did is rearranged how the threads are accessing the data in order for us to first minimize the control divergence, and then second also have coalesced memory access keys. So here, when these threads all access their first element, these first elements are all next to each other, and then when these threads all access the second element, these second elements are all next to each other. We then saw that we repeatedly reuse the same memory locations. So what we did is we used after the first initial load from global memory, we continued doing the reduction tree in shared memory, and we also saw that doing reduction in parallel actually has this overhead of doing a block-wide synchronization, and also of this control divergence that we have towards the end of the reduction tree. So what we did to minimize that price of parallelization is applied thread coarsening. So if the hardware was going to serialize our thread blocks anyways, we could just have one thread block of multiple thread blocks, where the thread block would initially do a sequential reduction across the thread blocks until it has enough elements for one element for each thread, and then it would continue doing the reduction tree in shared memory. And the advantage of this is that this initial phase where the block loops over, goes through more elements, this initial phase does not require synchronization across threads, and it also does not require you the intermediate results can be placed in register. And here we analyze the benefits of coarsening. We saw that if the blocks are all going to get executed in parallel, then we need log n steps, and each step needs a synchronization, so we need log n synchronizations. But if the hardware was going to serialize my blocks by a factor of c, then the execution time is going to be around c times log n steps, and I'm going to need c times log n synchronizations on the critical path of the execution. And the reason is that each thread block needs log n steps and log n synchronizations, we're executing thread blocks one after the other. On the other hand, if we coarsen the thread blocks, then rather than having log n steps and log n synchronizations, we're going to have an initial phase where we do a sequential accumulation without any synchronization, and that's going to require 2 times c minus 1 steps. And then at the very end, we're going to have log n steps and log n synchronization. So you'll notice that coarsening reduces the number of synchronizations that I need to make, and also reduces the number of steps that I need to take. So this was a quick overview of what we covered last time. Any questions before we move on to talking about scan today? Okay. Well, then today we're going to talk about scan. In particular, we'll look at the Kogge-Stone method for doing parallel scan, and next time we'll look at a different method. And we're also going to cover an optimization we haven't seen before, which is double buffering. So let me start by introducing what scan is. So a scan operation is an operation that takes an input array. So this input array can be x0 to xn minus 1, and an associative operator. And this associative operator could be anything. It could be sum, product, minimum, maximum. And what the scan operation does is that it returns an output array y0 to yn minus 1. And there's two versions of scan, inclusive and exclusive. In inclusive scan, every element in this y array is going to be the combination of all the elements in the x array up to the same index. So for example, yi is going to be x0 up until xi, all combined with each other using this associative operator. In exclusive scan, every element in y, so yi is going to be the combination of all the preceding elements, but not including I. So here yi is going to be the combination of x0 to xi minus 1, but not including xi, whereas inclusive scan includes xi. So let me show you an example of what I mean by this. We'll start with addition. So an inclusive scan in the context of addition looks like this. The first, I have an array that has these values over here. The first element in the result output array is going to be just the correspond to the element in the input array. The second element is going to be the sum of the first and the second element. The third element here, 16, is going to be the sum of 3, 6, and 7. The fourth element, 20, is going to be the sum of 3, 6, 7, and 4, etc. Okay. On the other hand, with exclusive scan, in the output array, the first element is going to be 0. The second element is going to be the sum of the preceding elements, but not including the corresponding elements. So it's going to be the sum of just 3. 9 here is going to be 3 plus 6, but we don't include 7. 16 will be 3 plus 6 plus 7. 20 will be 3 plus 6 plus 7 plus 4, etc. So every element is going to be the sum of all the preceding elements, but not the corresponding element. This is what exclusive scan is. In general, if we have an array x0 to x7, then in inclusive scan, every element is going to be the combination of all the preceding elements and the corresponding element. So in this case, this value will be x0 to x3. And in exclusive scan, the initial value will be the identity value, and then every element will be the sum of all the preceding elements, not including the corresponding elements. So here, the value of y3 is going to be x0 to x2. So it's x0 to x2, but not including x3. Okay, so this is what the scan operation is. As you can see, it's actually quite a sequential operation, but there are actually good ways to parallelize it. Let's look first at how we do a scan sequentially. So a sequential scan for sum is going to look like this. In the inclusive scan case, the output of 0 is going to be input of 0. All right, and then we're going to loop over the elements from 1 to n, and then output of I is going to be output of I minus 1 plus input of I. Okay, so in other words, output of 1 is going to be output of 0 plus input of 1. Output of 2 is going to be output of 1 plus input of 2, etc. With exclusive scan, we're going to initialize the output to 0, and then we're going to do output of I is equal to output of I minus 1 plus input of I minus 1, as opposed to input of I over here. Okay? And in general, this is what the inclusive scan and the exclusive scan look like. Again, here, instead of 0, we have the identity value, and instead of addition over here, we just have whatever operator we are using to define our scan operation. Okay? Is it clear what scan does to everyone? Anybody have any questions? Okay. So similar to reduction, when we do scan in parallel, we're going to have to synchronize across threads. And because we need to synchronize across threads, we can't do a global scan across the entire GPU. So what we do is we typically do a segmented scan. So similar to reduction, threads must synchronize to perform scan, and we cannot synchronize across thread blocks. So the solution is to use a segmented scan. The textbook also refers to this as a hierarchical scan, where every thread block scans a segment, and then we scan the partial sums, and then we update the segments based on the partial sums. So this is what it looks like. If we have some input, every block is going to take a segment of this input, and it's going to perform a scan on this segment. So every block has a scanned version of the array. And then every block is going to store a partial sum, which is going to be the sum of all the elements in their segment into some array. Okay. And then what we will do is we will scan these partial sums. Okay, so here each sum over here corresponds to the sum of the blocks. So what we do is we scan the partial sums. So now this element corresponds to the sum of all the elements in block 0. This element corresponds to the partial sum of block 0 and block 1. In other words, it corresponds to the sum of all the elements in block 0 and block 1. This element here corresponds to the scan of the partial sums. So it's the of blocks 0, 1, and 2. In other words, it's going to be the sum of all the elements in blocks 0, 1, and 2, etc. And then what we do is we have to go back. So here to block 1, we need to add the sum of all the elements in block 0, which is this value over here. In block 2, we need to add the sum of all the elements in block 0 and block 1, which is going to be this element over here, etc. So what we do is we take these scanned partial sums and then we add them back to all the elements in each of the blocks results, so that we have the final scanned array. Okay, so we do a local scan, and then we produce a partial sum for each block. We scan the partial sums, and then each block takes the partial sum of the previous blocks and adds it to its own element. Notice here how block 0 is not going to add anything because block 0 doesn't have any blocks before it. But here block 1 is going to add the partial sum that corresponds, this partial sum here, which corresponds to the block 0 value. Block 2 is going to add this partial sum, etc. Okay, so now we know how to segment scan and do it in different blocks in parallel. So what remains is how to implement a parallel sum in each block. And this is what we'll be talking about for the rest of today. But before I move on, is the idea of a segmented scan clear to everyone? Someone's asking, this one is inclusive? Yes, you can think of this as being inclusive. Actually, over here, I intentionally did not draw an arrow from a specific element to a specific block because I wanted this figure to be general enough to work for inclusive and exclusive. But yes, whether it's inclusive or exclusive will impact what element we're going to use when we access this partial sum array to accumulate the final result of these blocks in the second phase. Okay.
Professor, we could implement this recursively if it was like a CPU to have good performance, but on GPU that wouldn't work.
So what we usually do is we can do the recursion. So here, these thread blocks, when they store their partial sums, they all need to wait for these partial sums to be scanned before they can accumulate their partial sums to their element. So here, these thread blocks are not. We're not going to do the recursion on the GPU. Okay, so these thread blocks are going to go away because the only way we can synchronize across all the thread blocks is by terminating the kernel and launching a new one. So here, what can be done is we have a grid that that does these local scans and produce these partial sums array. But then when to scan this array, we can recursively call the stub function on the CPU so that we perform a scan for this array on the GPU. Okay, so this is how we can use recursion to do. So yes, we can use the recursion, but as you said, we're not going to do it on the GPU. Instead, we will do the recursion on this with the stub function.
I see. Okay, thank you.
Yeah, you're welcome. Okay, so having said this, let's proceed and see how we can do a parallel scan inside of each thread block. And the algorithm we're going to use is called the Kogge-Stone parallel algorithm, and in particular, we're going to use the inclusive scan first. So we're going to start with inclusive scan, and the way the Kogge-Stone algorithm works for doing a parallel scan is as follows. I'm going to start off with this array x0, x1, x2 to x7. I'm going to assign a thread to each one of these values, okay? And then in the first iteration, what's going to happen is every thread is going to add the element it owns to the previous element, the element that's 1 to the left. Okay, so at the end of this iteration, you'll notice, obviously for x0, there's no element to the left, so we won't do anything with x0. But here for x1, now we have x0 to x1, so this value is complete. For x2, we have x1 to x2. Okay, so it's not complete yet. But now each value is going to consist of itself and the value to itself. Well, now what we observe is that here x1 to x2, here I need to have x0 to x2, so I'm still missing x0. Over here, x2 to x3, I still need to have x0 and x1, so I'm still missing x0 and x1, right? And here x3, x4 needs more than that. It needs more than just 2 elements. But what we can do next, if we just want to complete these 2 elements, is we can have every thread, rather than adding the element that's 1 to its left, it adds the element that is 2 to its left. So here every thread is going to now add the element that's 2 to the left. So here to x1 and x2, this thread that owns x1 and x2 is going to add x0. The thread that owns x2 to x3 is going to add x0 to x1 so that we get x0 to x3. And now we have these first 4 elements are complete, and we have these remaining 4 elements are incomplete. Okay, but all the threads are going to add the element that's 2 to the left. Okay, now in the next iteration, what we will do, well, we observe here that this partial sum, x1 to x4, just needs x0 so that we can have the x0 to x4. So all we need is x0. This partial sum here, x2 to x5, it just needs x0 and x1, which is over here. This over here, x3 to x6, it only needs it needs x0 to x2, which is over here, etc. So what we can do finally is that every element is going to add the value that is 4 to its left, okay, to get the next result. And you'll notice that with 3 iterations, we are done performing the scan. Okay, so we have an array of 8 elements, and we were able to perform the scan in parallel using 3 steps, which is log 8. Okay, so with log n steps, we were able to perform the scan in parallel. Any questions about this approach? Is it clear to everyone? So basically, all the threads work. In the first step, each thread adds the element that's 1 to its left. In the second step, each thread adds the element that's 2 to its left. In the third step, each thread adds the element that's 4 to it. Clear? Okay. Well, if everything's clear, let's go and implement. So over here, I started us off with some code. Here, what the scan does is that we allocate the partial sums. So here the CPU is taking care of the segmented scan stuff. So here I allocate the partial sums. I call the scan kernel, and then you'll notice here if I have one thread block, that means I'm done. So I just do the addition. If I have if I have more than one thread block, then I call the stub function recursively until I'm down to one thread block. And once I'm down to one thread block, that means I'm done and I can go back. And after I return from scanning the partial sums, I call an add kernel that's going to add the partial sums for each thread block. Okay, so this code over here is basically taking care of that segmented scan that I told you about. I have two kernels. The second add kernel takes care of the part where after I scan the partial sums, I go back and for each thread block I add to it the partial sum that it needs to add to all of its elements. So what's left is for me to implement this scan kernel to follow this Kogge-Stone parallel include. Okay, so let's do that. The first is for each thread to identify the input element that it's responsible for. And you'll notice that unlike reduction, here in scan, every element has a corresponding thread. Okay, in reduction, we had every other element had a thread that owned it, or in the coalesced version, the first half of the elements had threads and the others did not. But here in scan, every element is going to have a corresponding thread. So finding out what element a thread is responsible for is nice and simple. We just do unsigned int I equals block index.x times block dim.x plus thread index.x. Okay? So now every thread has a corresponding element that is responsible for in the input. What I'm going to do first is I'm going to move, I don't want to modify my input. You'll notice here I'm modifying the values in place. I don't want to modify my input array. So what I'm going to do for starters is I'm just going to move all the input values to the output array, and then I'm going to work inside of the output array. Okay, so I'm going to just write output of I is equal to input of I. Okay, so I'm going to move all my input elements to my output array so that later on I perform this scan in my output array. Okay, and I'm also going to sync threads here because you know this thread is moving is x1 from the input array to the output array, but then this thread and this thread both need to access x1 in the first iteration. So I need to sync threads to make sure that this thread finishes moving x1 from the input array to the output array before this thread tries to access it from the output array. Okay, so I have a sync thread. So now I can begin my loop that does the reduction for me. And I'll notice, just like with reduction, where the stride was a convenient index to use for the loop, we're also going to use the stride here as the index of the loop. So you'll notice in the first step, the stride was 1. In the second step, the stride was 2. In the third step, the stride was 4. Okay, so so basically, the stride is going to start at 1, and we're going to multiply it by 2 every time. So I'm going to have a loop that goes from unsigned int stride equals 1. Stride, where does stride end? Well, let's take a look. Here, every thread block has 8 elements, and we go with a stride of 1, 2, and then 4. We stop at 4 because by the time we get to 4, all the threads have the results ready. And obviously, we can't have a stride of 8 because for any of these threads, a stride of 8 is just going to take out of bounds. Okay, so for 8 elements, we stop at a stride of 4. In general, for block dim elements, we're going to stop at a stride of block dim over 2. Okay, so we're going to have stride less than or equal to block dim over 2, and we are going to multiply stride by 2 on every iteration.
Doctor?
Yes?
Why don't we put the output elements in the shared memory? Well, we will.
Well, that's a very good observation. So it is a good idea to put the output elements in the shared memory. But because for pedagogical reasons, we're doing things one step at a time. So you're absolutely right. It's a great optimization to put the output elements in shared memory. In order for me to kind of take things one step at a time and also to show you what is the incremental improvement of putting things in shared memory, I'm starting by working in global memory, and then the first thing we're going to do is we're going to put it in shared memory. Okay? So, but yeah, that's a great observation that we should put it in shared memory. Okay. After we've now we have this loop that goes through our stride. Now, what are we going to do on every iteration? Well, let's take a look. On every iteration, what we will do is we're going to add the element that is stride to the left. Okay. So in other words, we're going to do output of I is plus equals output of I minus stride. Okay. Output of I equals output of I minus stride. So for each element, we're going to add to it the element that is stride to its left. Here we add the element that's 1 to the left. Here we add the element that's 2 to the left. And then here we're adding the element that's 4 to the left. Okay? But you'll notice that not all the threads compute on every iteration. Only the threads that whose so here when the stride is 1, only threads 1 to 7 compute. When the stride is 2, only threads 2 to 7 compute. When the stride is 4, only threads 4 to 7 compute. Okay, so in general, for any value of stride, the threads that compute are the threads that are going to be, whose index is going to be greater than or equal to the stride. Okay, so we're going to need to have a boundary check over here where we write if, and again, we're doing this on a per thread block basis. So here the index that we're going to compare is the local index of the thread block, not the global index. So here we're going to check if thread index.x is greater than or equal to stride, then we're going to do output of I plus equals output of I minus stride. Okay?
We also need one to not go out of bounds, right?
That we can in this I'm not worried about if you mean out of bounds at the very end of the input. In general, in these lectures, you've noticed that I haven't been worrying about the out of the bounds at the end when I'm implementing the code, just because I like to leave something for you to do in the assignment. So yes, we would need to have a check for when the very last elements are out of bounds, but that is something that you can do as an exercise in the assignment, and we are kind of intentionally not covering that in the lecture. Okay. Okay, so we do this. Now, one thing to note is that on each of these iterations, right, we need to wait for all the threads to finish writing their updated values before proceeding to the next iteration, where the threads start reading the new values. So how do we get all threads to wait for each other on each iteration? What do we use? Come on, guys, how do threads? Right, sync threads, right. So we're gonna have to use is on every iteration, we're gonna need a sync threads to make sure that the threads wait for each other before they proceed. Okay, and then what we need to do once we are done is that the last thread is going to have the sum for all the elements of the thread block. So this last thread is going to need to take this result and store it in the partial sums array so that when we do a scan of the partial sum array, that value is there. So how do I check if something is the last thread? I'm going to do if thread index.x is equal to block dim. I could have wrote block dim.x as well, block dim minus 1. Okay, and if thread index.x is equal to block dim minus 1, then what I'm going to do is I need to take the partial sum of the last thread, and I'm going to store it as the partial sum for the entire block. So I'm going to write partial sums of block index.x. So the partial sum for this block is going to be equal to the value that is owned, the output value that is owned by this thread. So it's going to be to output of I. Okay? Is this clear to everyone? Any questions? Okay. So then let's now compile this and let's run it. Okay. Okay, let's run it again. Oh. Okay, so somehow this actually worked, but it was not supposed to work. So maybe we just got lucky, and this worked. Okay, so somehow we got lucky and this worked, but not supposed to work actually. This was not supposed to work, and there's a reason why this was not supposed to work. And the reason is that over here, when I read output of I minus stride and I add it to output of I actually have a race condition. Okay, so this is incorrect. It's odd because I actually tested right before the class and this did not work. So I wonder why it actually does work. It did work now. Anyways, sometimes that's the thing about race conditions. Sometimes they happen and sometimes they don't. So, but if you run for enough times, eventually you might get into the situation where the code won't work. Let me show you why this code that we wrote does not work. So you'll notice over here. Let's focus on what these two threads are doing. So this thread over here reads x1 and it reads x0 and it writes x0 x1 in the output. So here both of these are the same array. Okay. Whereas this thread over here is going to read x1 and read x2 and store the result from x1 to x2. Okay. Now what's the problem here? The problem is that if we write our code like this, where I just do output of I plus equals output of I minus stride, if this thread over here, thread 1, reads x0 and x1 and then writes the result of the addition x0 to x1 before this thread over here reads x1, then we have a problem. Okay, and the problem is that if this thread reads x0 and x1 and then stores x0 to x1 in its place, when this thread comes to do the reading, it's actually going to read x0 to x1. It's not going to read x1. Okay, so what we need to do is we need to make sure that this thread 2, reads x1 before we allow thread 1 to write the updated value of x2. Okay, we need to make sure that thread 2 reads x1 before we allow thread 1 to update x2. Okay, so what we're going to do is we're going to read it, we're going to sync, and then we're going to write, and then we're going to sync. Okay, so here we need to make sure that every thread is going to read output of I minus stride before we allow the thread that owns output of I minus stride to update it when we do output of I plus equals the result. Okay, so we're going to separate the statement in two. We're going to create a temporary variable. Let's call it v. Okay, we're going to read output of I minus stride. Okay, we're going to sync threads. Okay, and then we're going to update output of I by adding to it the old value of output of I minus stride. Now we have a problem here, and the problem is that I cannot have sync threads inside of this if condition. Why can't I have the sync threads inside of this if condition?
Because some threads that won't go in will synchronize with the later sync thread, so it's going to mess everything up.
Right, so not all the threads are going to take this if condition. And whenever I have sync threads, I need to make sure that all of the threads can actually reach the sync thread. So actually, it's not going to be the case that some threads will reach this one and some threads will reach this one and they'll sync. That's not the way CUDA works. In CUDA, every sync thread is its own barrier. So different threads reaching different sync threads doesn't mean they will sync together. Okay, so in this case, if you put a sync threads in a place where you have control divergence, if you put a sync threads in a place where not all the threads in the block are guaranteed to reach, you'll actually just have undefined behavior. And what that means is that the compiler gives you no guarantees that it will produce correct results for your program. Okay, so what we need to do is we need to actually put the sync threads outside of the boundary check. So we're gonna close the boundary check here, and then we're gonna sync threads, and then we're going to do the check again. Okay, so we read the value, we sync threads, and then we update the value. Okay, so this actually is correct. Okay, and now I'm going to compile this, and I'm going to run it, and it produces a correct result. The other one luckily produced correct results, but it was not supposed to. The previous implementation was not correct. Okay, you'll notice over here that the kernel, the GPU kernel, is called multiple times, and that's because you remember we have this segmented scan, and then we were recursively calling the kernel again to do the scan for the partial code. So here we did 3 different scans. Of course, the first scan was the one that took the most amount of time because that's the one that had the largest array. These here were small because they were just scanning the partial sums array, which are much smaller than the original. Okay, so on the CPU it takes around 50 milliseconds. On the GPU it took around 8.4 milliseconds, plus all this other stuff. In total, the GPU time actually took longer than the CPU time in this case. However, if your array is already on the GPU, you definitely want to, this time, a lot of it is the copy time, right? A lot of it is copying to the GPU and then copying back from the GPU. But if you eliminate the time it takes to copy to the GPU and copy back from the GPU, then the time that it takes to do the scan on the GPU is substantially faster. So if your data is already on the GPU, then you definitely want to do your scan on the GPU, and it will be much faster than doing it on the CPU. Okay.
Doctor? Doctor?
Yes, question?
In what cases do we have the data already on the GPU?
So if I'm writing this large code for doing simulation, simulating something, right? What I do is at the very beginning of my application, I copy the initial data to the GPU, and then I run all the different computations on the GPU. I launch many kernels to do many different operations, and then in the final result, I bring it back to the CPU. Okay, so if I have an operation, a computation that I'm doing that does many different things, and one of those things is scan. Okay, I'm not going to copy to the GPU, do my first operation, then bring it back. Then copy again to the GPU, do the second operation, then bring it back. And then copy to the GPU, do the scan, and then bring it back, right? I'm going to copy at the beginning, I'm going to do all my operations on the GPU, and then I'm going to bring back the result. Okay, so in this case, usually with these long running applications, there are many kernels that run on the GPU, one after the other. And that's why the copy time is usually advertised across all the benefit that we're going to get for all of these kernels. Okay, but if all we're doing is just doing a scan, which is not typically the case, then yeah, maybe it's better to just do it on the CPU. Have I answered your question?
Yes, thanks.
Yeah. Another example, for example, is like if you have a neural network with many layers, right? You're gonna have a kernel that executes each layer, right? But you don't need to copy. The output of one layer is the input to the other layer, so you just keep that on the GPU. There's no point in copying back the output of the layer to the CPU and then copying it back to the GPU as the input of the next layer and running the kernel for the next layer, right? You just keep the output of the previous layer on the GPU as the input to the next layer. Somebody was asking if I could repeat the issue with syncing inside the if statement. Yes. So here, if I did not have the if statement, if I did not have the if statement, I just had this. The problem is that not all the threads in the block are going to come inside of this if statement. So not all the threads in the block are going to reach the sync threads. However, sync threads requires that all the threads in the block reach it. And that is why if I put sync threads inside of an if statement like this, I'm going to have undefined behavior. Is that clear?
Professor?
But wouldn't the threads that don't go into the if be already like inactive and not doing anything?
Right, and that's a problem because sync threads means that all the threads in the block need to reach it. So if some of those threads are inactive, they're not going to reach the sync threads. Okay, but you know that's not necessarily you know what actually happens. The semantics of sync threads are that wherever you have a sync threads, all the threads in the block need to be able to reach that sync threads. If you put a sync threads in a place where not all the threads in the block can reach it, then this will result in undefined behavior. Okay, because the compiler might make the assumption that all threads can reach that sync threads, and that will impact how the compiler will generate code. Okay, so you should always put a sync threads in a place where all threads in the block can reach it. Otherwise, there's no guarantee that the compiler will give you correct code.
Professor, but like if we're not, if the sync threads are not confused in between each other, do they have some sort of ID number or like some sort of number
so that you know that would be kind of that's related to the hardware implementation and how the hardware implements sync threads. So there's going to be some kind of resource that is needed to support being able to do a synchronization, right? And maybe each of these sync threads is going to have its own resource or not, right? But the point is that each sync thread is its own barrier. And if this sync threads is different from this one, if some threads reach this one and some threads reach this one, that doesn't mean they're syncing together. Okay, it's different from you know other parallel programming models, for example, like MPI, where if you do a synchronization, different ranks reaching different MPI calls might be able to synchronize together from different calls. That's not the case in CUDA. In CUDA, only threads synchronize with each other via the same call, not via different.
I see. Okay, thank you.
Yeah, you're welcome. Okay, let's go back to our correct code. Okay, so having said that, let's now, so we said our solution is to wait for everybody to read before we do any writes. And this is what we did, and we saw that this gave us correct code. So this is great. Now we have a kernel that does scan. So now let's look at how we can optimize this kernel. And as one of you said, one of the first things that comes to mind is what we did with reduction, and that is to use shared memory. So you'll notice here that the memory locations are reused. So rather than doing all of this inside of global memory, what we can do is we can load the initial values into shared memory, and then do our scan in shared memory, and then store the final result to global memory. And we can do that, and let's see what performance benefit that gets us. So here, rather than loading from the input to the output, okay, we can load from the input to a shared memory buffer, and then we can do all of this inside of the shared memory buffer, and then we can store to the output at the very end. Okay, so let's write the code that does that. So I'm going to start by creating a shared memory buffer I'm just going to call it buffer underscore s. How big is this buffer going to be? Remember that the number of elements that a thread block owns corresponds to the number of threads in the block. Okay, so we're just going to have block dim elements. Okay, next what we do, instead of loading to the output, instead of loading input of I to output of I, we're going to load to the buffer itself. Okay, so we're going to load to the buffer. And of course, when we load to the buffer, we're not going to use the global index of the thread to access the shared memory buffer. We're going to use the local index of the thread to access the shared memory buffer. Okay? So now that we've done this, now all the places where we were accessing the global array, global output array, we should go and we should use the buffer instead. So here, instead of output, we're going to have buffer underscore s, and instead of I, we're going to use thread index.x. By the way, this now should make this boundary condition much more clear, right? So here, I'm accessing my shared memory buffer with thread index.x minus stride, which means that thread index.x minus stride should be greater than or equal to 0, which means that thread index.x should be greater than or equal to stride. Okay? And then over here, I'm going to use buffer underscore s, and I'm going to index it with thread index.x. And then down here, I will also use buffer underscore s, and I will index it with thread index.x. Okay, and then of course, finally, I do need to eventually write to my output array. So I will also write output of I is equal to buffer underscore s of thread index.x. Okay, and with this, what we've done is we have changed our code so that we use a shared memory buffer throughout the computation, and then at the end we write to to the output. Okay, is this clear to everyone? Any questions? Okay, let's run this code. Remember before, it took us about 8.4 milliseconds to do the largest scan kernel. So now let's compile and let's see what performance improvement using shared memory has given us. So now we're down to 6.4 milliseconds from 8.4 milliseconds. So that's around a 25% improvement, which is quite nice. Okay, let's improve this further. So this is the shared memory code that we wrote. Now, one observation is that every loop iteration, we've had to use sync threads twice, which is different from reduction, where we used it once per iteration. And remember, what was the reason we're using sync threads twice? Well, the reason was that we need to read and make sure everybody reads before we let anybody write. Well, one optimization to avoid syncing twice is by using two different buffers. One and having the problem here, the main problem is that I'm using the same buffer as both an input and an output. Okay, so what we can do is, if we want to eliminate the synchronization, is to use a different buffer for both the input and the output. And let me show you what that would look like. So this optimization I'm about to introduce is called double buffering. And the idea of the optimization is to eliminate one of the synchronizations by using two buffers and then alternating between them. So on each iteration, we swap what the input and the output are. So on the first iteration, what we're going to do is we're going to read from one of the buffers, but we're going to write to another buffer. Okay, so in this case, the input is going to be, so I'm going to have two buffers, buffer 1 and buffer 2. And in this step, the input is going to be buffer 1 and the output is going to be buffer 2. Now, one thing you notice here is that later on, I'm going to need x0. And here, buffer 2 doesn't have x0. So what I will need to do when I use two buffers is I will need this thread that was previously inactive will actually have to participate, and it will have to just transfer x0 from buffer 1 to buffer 2 without doing any addition. Now on the second iteration, buffer 2 is going to become my input, and buffer 1 is going to become my output, and I will again read from my input and store to my output, okay? And because I'm using a different buffer for the input and the output, I don't have to worry about, over here, I do not have to worry about this thread writing to x1 before this thread read from it, because this thread wasn't writing to buffer 1, was writing to buffer 2. Similarly, over here, I don't have to worry about this thread over here writing to this location before this thread read from it, because this thread is not going to write to this location. It's going to write to buffer. Okay, so we're going to read from buffer 2. We're going to write to buffer 1, and then the threads that are inactive, we still need to make sure that we have these results in our buffer. So the threads that were previously inactive are just going to transfer the value as is to buffer 1. And we also do the same thing at the end. At the end, buffer 1 is going to be our input, buffer 2 is going to become our output, and we're going to read from buffer 1, and we're going to write to buffer 2. And then the threads that don't do any addition are just going to have to transfer the value from buffer 1 to buffer 2. Okay? So by doing this, what we do is we alternate the input buffer and the output buffer every time, so that we're never reading and writing from the same place at the same time. And what that does is that it eliminates this the need for me to have to synchronize between the reading and the writing. Is this clear? Is it clear why using two buffers eliminates the need to synchronize between reading and writing? Any questions about this? Okay, well, if it's clear, let's go and implement this and see what performance improvement it gives. So I'm going to switch to the terminal. So here, rather than having one buffer, okay, rather than having this one buffer, okay, instead, I'm going to have two buffers. I'm going to have a buffer 1 and a buffer 2. At each time, one of them is going to be my input buffer, and one of them is going to be my output buffer. So to make things easy for myself, I'm going to create a pointer. I'm going to call it in buffer, and I'm going to initialize it to buffer 1. Okay, so now in buffer points to buffer 1. And I'm going to create another pointer. I'm going to call it out buffer, and I'm going to initialize that to buffer 2. Okay, so now in buffer is going to point to buffer 1, and out buffer is going to point to buffer 2. Just like here initially, the in buffer was buffer 1, and the out buffer was buffer 2. After that, I'm going to put my result. I'm going to load my input initially to the input buffer. So here I'm going to use in buffer. Okay. Then down here, okay, instead of doing all of this, okay, all I need to do is to load from the input buffer and add and then store to the output buffer. So here, remember, our condition was if thread index.x is greater than or equal to stride, okay, then the result in the output buffer is going to be the result in the input buffer plus the result in the input buffer minus stride. Okay, so here, out buffer underscore s of thread index.x, okay, is equal to in buffer underscore s of thread index.x plus in buffer underscore s of thread index.x minus stride. Okay, so what I'm going to do is I'm going to put in the output buffer the sum of the element, the corresponding element to the input buffer, and the element at thread index.x minus stride. This is what I'm doing over here. Okay, but there's something important that I also need to do. What is that?
Else transfer the value as it is.
Right, exactly. So here, threads that were previously not doing anything, now these threads are playing an important role. Now these threads need to take the value and transfer it as it is. So here I'm going to need to have an else. Okay, and in this else, I'm going to have to write output buffer is just equal, output buffer of thread.x equals input buffer of thread.x. Okay, and now I do a sync threads. And the nice thing here is that I only have to sync threads once. I don't have to do sync threads between the read and the write. Okay, now I'm not done. What do I need to do after I do the addition?
Swap pointers.
Right, I need to swap the buffers. So now in the next iteration, my end buffer is going to become buffer 2, and my out buffer is going to become buffer 1. So I need to swap in buffer and out buffer. So I'm going to just create a temp pointer, call it temp. I'm going to write in, I'm going to write, well, I'll initialize, I'll save the pointer, the value of end buffer, and then I'm going to write end buffer underscore s is equal to out buffer underscore s, and then out buffer underscore s is equal to temp. Okay, so now I swap the buffers. So in every iteration, I'm going to use the buffers to do the addition, and I'm going to swap them. I'm going to use the buffers, and I'm going to swap them. Okay, until I'm done. Once I'm done, I come down here, and what I need to do is I need to now store the total sum in the partial sums array. Okay, how do I do that? Which buffer should I use? In buffer or out buffer?
In buffer.
Right, I need to use in buffer. You know, even though at the very end I put the result in the out buffer, right? But the last loop iteration here actually swapped them again. So I should use in buffer to get the final result. Okay, and I will also use in buffer over here to put the final result. Okay, so this double buffering, essentially what it has done is that it saved us one sync threads inside of this loop. So now every loop iteration, rather than doing 2 sync threads, I'm doing 1 sync thread. So let's see how much performance improvement this gives us. I'm going to compile. Oops. Okay. So here I accidentally used the capital S. This should be a lowercase. Okay, let's compile. So remember, last time without double buffering, the time of the kernel was 6.4 milliseconds. So now we're going to run, and now you'll notice that our time is down to 4.4 milliseconds. Okay, so again, this is a significant performance improvement from having applied this double buffering technique. Okay, any questions about double buffering? Is it clear to everyone? So again, what we did is we created 2 different buffers instead of 1. And we every time one of these buffers was the input and one of them was the output. And we swapped them on each iteration. And double buffering, you know, it's an optimization that's used commonly in many different places where you have an input and an output, and you constantly alternate between them. Sometimes we use it to save memory because instead of allocating a buffer for every intermediate result, you just continuously alternate between 2 buffers. But in this particular case, we used it to reduce synchronization, and we actually used more memory in order for us to reduce okay, so this is the code that we wrote, and with that, we've done taking a look at how to implement inclusive scan. What I'd like to do is just to look at how exclusive scan differs. So for the Kogge-Stone algorithm, exclusive scan, we can just formulate it as an inclusive scan, right? So to do an exclusive scan, we can simply shift the elements by 1 when we load them to shared memory. And then we just do an inclusive scan for the shifted array, okay? And then the last element that we were supposed to get, that will only be used for computing the partial. Okay, so in other words, to do an exclusive scan. Well, actually, let me first do the exclusive scan on the CPU. So here, for an exclusive scan on the CPU, rather than initializing the output of 0 to input of 0, we're going to initialize output of 0 to just 0. Okay, and rather than doing output of I equals output of I minus 1 plus input of I, output of I is going to be output of I minus 1 plus input minus 1. Okay, because in the exclusive scan, output of I does not include input of I. It includes up to input of I minus 1. So here I've modified the CPU code to do an exclusive scan. Notice it's much easier than the modifications we're about to do to the GPU code. In the GPU code, the way I'm going to do an exclusive scan for the Kogge-Stone algorithm is I'm simply going to shift my input by 1. So here, rather than loading input of I to my buffer, I'm going to load an input of I minus 1. I'm going to shift my input to the right by 1. Okay, so here, I'm going to do in buffer of input of I minus 1. Okay, however, I can't do this for the very first element. For the very first element, because there's no I minus 1 for the very first element. So for the very first element, what I will do is I will just load 0. I'm going to do this on a per thread block basis. So I will write if thread index.x equals 0. So the first thread in the block, for the first thread in the block, I'm going to load a 0. And for the remaining threads, I'm going to load the previous element. Okay, so here for the first thread in the block, I will put a 0. And for the remaining threads, I will load the previous element. And now what I have is I have a shifted array. I've taken the segment that the block is responsible for, and I've shifted it by 1, and I've put a 0 at the beginning. And now I'm just going to do what I did before. I'm going to do an inclusive scan on the shifted array, which is basically an exclusive scan on the non-shifted array. Okay. So this is yes, question.
Yeah, couldn't we have loaded the whole thing shifted by 1 to the GPU?
Yes, you could have loaded the whole thing shifted by 1 as well. The part of the problem is that the code I've written here, and especially the recursive code that I've written to do the partial sums, is kind of working for inclusive scan. So that's why I'm doing it. Okay, because I'm trying to have as minimal changes to the inclusive scan code as possible. So over here, after we do this, down here in the partial sums, when we add the partial sums should include all the elements in the block segment. Okay, but now that I've shifted by 1, the last element in the block segment is not going to be included in the total sum in the last element. So what I will do is over here, I will need to add to this input of I. Okay, because the last thread in the block is going to load input of I minus 1. And the first thread in the next block is going to load 0. Okay, so input of I is not going to be accounted for anywhere in this code. And the way I account for it is it's going to go into the partial sum, and I account for it by adding it here to the partial. All right. So now that I've done this, every thread has done its own exclusive scan, and it has also found its partial sums and put it in the partial sums array. And now when I do the recursion, I'm going to do an exclusive scan on the partial sums array. Okay, but if I've done an exclusive scan of the partial sums array, now when the thread block comes to add the sum of the previous blocks to its elements, now the sum of the previous blocks is not going to be the sum of the previous blocks in the scanned partial sum array is not going to be here when we do the add. In the past, what I was doing is I was getting when I was doing inclusive scan, I was getting the partial sum. This is the scanned partial sums of the previous thread block because I wanted to add the sum of all the previous blocks to my element. But now in exclusive scan, the sum of the previous thread blocks is actually at block index.x, not in block index.x minus 1, because when I scan the partial sums array, I used an exclusive scan. So here I will also need to remove this minus 1 from here in order for me to do the So with these simple modifications, we've converted our inclusive scan code to do an exclusive scan. And what one of you has mentioned is also correct. Another way to have done it is simply to have shifted the global array by 1 and done an exclusive scan of the global array. So that's another possible way of doing it. Okay, and then after having done this, let's compile and run. We're going to compile and run, and see that the code succeeds and also has similar performance. Okay, so this is how we support the exclusive scan. Now, the final topic I'd like to talk about today is something called work efficiency. Okay, something called work efficiency. So a parallel algorithm is said to be work efficient if it performs the same amount of work as the corresponding sequential algorithm. Okay, so we say a parallel algorithm is work efficient if it performs the same amount of work, and by work here I mean so in the case of scan, the number of floating point additions that we perform. Okay, so it's work efficient if it performs the same amount of work as the corresponding sequential algorithm. Okay, now let's reason about the work efficiency of scan. Okay, how many additions does the sequential scan perform?
N or the less.
If I want to scan an array of n elements, how many additions does it perform? Sorry, somebody was answering.
N.
Right, n additions, right? So here, if I go, oops. So here, if I look at my sequential scan, I just have a loop that goes around n times, okay, and I do an addition every for each of these loop iterations, okay. So the sequential scan performs n additions, okay. What about the Kogge-Stone parallel scan? How many additions does the Kogge-Stone parallel scan perform? Okay, well, let's take a look. Let's go back to our illustration. So here in this illustration, how many steps do we have, first of all? So here are n, the number of input elements. So here n is 8. So how many steps do I have? I have log n steps. Okay. In the first step, how many additions do I perform? I do n minus 1 addition, right? In the second step, I do n minus 2 addition. In the third step, I'm doing n minus 4 additions, etc. Okay. So I have log n times, well, I have n minus 1 plus n minus 2 plus n minus 4 plus n minus 2 to the power of the iteration, right? And I do that log n times. Okay, so if we go down, we go back down to our reasoning about our work efficiency, we're going to have log n steps, and every step we're going to do n minus 2 to the power of step operations per step. Okay, in other words, we're going to do n minus 1 plus n minus 2 plus n minus 4 dot 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 plus n minus n over 2. Okay, and how many terms do I have here? I have log n terms because I have log n steps. So the final result is going to be n plus n plus n plus n log n times. So that's n log n, and then minus 1 plus 2 plus 4 plus dot 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 plus n over 2. That comes out to n minus 1. So in total, I'm going to do n times log n minus n minus 1 operation, which is O of n log n operation. So my sequential scan performed only n addition, whereas my Kogge-Stone parallel scan actually performed n log n addition. Okay, and what that means is that my parallel algorithm is not performing the same amount of work as my sequential algorithm, In other words, my parallel algorithm here is not work efficient. Now,
Professor, isn't
yes,
there
go ahead.
another, sorry, isn't there another n as well for adding the partial sums later on?
Well, over here, what I've assumed over here is that I'm doing the tree for the entire input. Okay.
Oh, okay, I see. That makes sense. Okay.
Yeah. So this n here is for the entire tree. But you know, if you work it out, right? Basically, when you're doing the partial sums, it's like you're continuing the tree. Okay. So it should still be kind of similar for when we did the segmented scan. Okay, so the algorithm, this algorithm here is not work efficient. Okay. Now, if all my thread blocks will actually run in parallel, okay, because remember, even though I perform this many operations, I'm actually completing the scan in log n step. So if all my operations are going to be perfectly parallelized, if they will actually be all be running in parallel, even though I'm going to perform more operations, I will do it in fewer steps. So I will finish faster. However, if my resources are limited, right, then the parallel algorithm might become quite slow because the parallel algorithm is actually doing more work than the sequential algorithm. It has lower work efficiency. Okay, so having made this observation, having seen that the Kogge-Stone algorithm has low work efficiency, okay, what we will do next time is we will look at a different parallel algorithm for scan that has better work efficiency, and we're going to compare the performance of these two algorithms. Okay, so if you'd like to read more about what we talked about today, you can refer to chapter 8 of the textbook. And the chapter 8 of the textbook also talks about the work efficient implementation, which we will be covering next time. Any final questions about today's material? Everything clear? All right. Well, then, if there are no final questions, then that's all for today, and I'll see you next time. Bye, everyone.